Hey, welcome back. Um, this is our fifth tutorial in the series. Hopefully you're getting used to the GLMs by now and R as well, the R environment. This week we'll cover now that we stepped through the sort of basic generalized linear models, we'll go through a little bit about checking assumptions and really model fit. Uh, these are two things that often get pushed aside in research articles. You don't see people report this a lot, which is sort of odd. Usually it's kind of put off to the side or a one sentence summary like, oh, we checked assumptions and they were fine. There's also a lot of myths out there and bad information about what you should do. And so what we're going to do is talk about some basic things that you should check anytime you've gotten your model somewhere where you think it's fitting well, but you just want to check. And this is a huge topic. There are textbooks on it. We'll just touch on brief things and not get too much into the weeds with it. I can recommend some other books under the video, and I'll do that. So what we're going to do is basically two things. First, we'll talk about looking at single cases or a group of cases or observations that don't seem to go with the rest of the data or are affecting the overall fit in a sort of too much. And so this falls under three terms that one of which is not really well defined, which is what is an outlier. But then two other terms that are a little bit better defined, influence and leverage, which in some ways can define an outlier, but other ways it doesn't. And then we'll talk a little bit about the checking assumptions. And again, the assumptions of ordinary linear regression are different from logistic regression. But generally, we'll see that one of the basic assumptions we want to look at is the linearity of the model, and do we have it right? Do we have the right set of predictors? And then do our residuals conform to, usually, at least in linear models, we would like our residuals to be uncorrelated with predicted values and with any value, any of the predictors that we have in our equation. And we also need them to have constant variance. And so sometimes when you're checking assumptions and you don't see either of those two things, it means that actually your model is incorrect. It's not that your model is bad, it's just that it's missing something. You failed to capture something important. The problem is that when we move to logistic regression and Poisson regression, the plots that we can make using or that we would use for OLS are not helpful, and we'll see why. And so we'll just look at those two. We won't worry about Poisson models, although it's covered in the text. You can kind of work on those as you see fit. And in general, it's really important to remember there's this sort of piece of advice is sort of a specific version of the, all models are wrong, but some can be useful, which is also kind of a misquotation from George Box, but that's the gist of it. And so Faraway says it's virtually impossible to verify that a given model is exactly correct. The purpose of diagnostics is more to check whether the model is not really grossly wrong. Indeed, a successful data analyst should pay more attention to avoiding big mistakes than optimizing fit. And the reason for that really, this last part really means that we don't want to have a model that's overfit to the data. That's more for prediction, but also for inference purposes, because then if we've totally overfit our model to data, it means it won't generalize. It means that we've somehow modeled the little idiosyncrasies that are in our data set, but that once we look at a different sample, those things might not hold. So we try to balance between wanting our model to fit enough to be useful, but not to be overfit so that it doesn't generalize. All right, so first we'll look at ordinary least squares. For this tutorial, you'll need both the faraway and mass packages, so I'll load those. And so the first thing that we're going to do is just take a look at this data set. You've used it before, so just as a reminder, we've got a few variables that we can use to predict gambling expenditures. So we'll use the sex of the respondent, socioeconomic status, their income in pounds per week, because this is England, their verbal score on a so-called intelligence test, and gambling expenditures. And we're going to change sex to factor so that it makes it a little easier to look at. So we fit this model already. Here it is again. So we see it looks like there's a drop in expenditure if you're female compared to male, controlling for the other variables. Same thing with income. As income goes up, your expenditures tend to go up. And then again, we have that adjustment down. There doesn't seem to be a strong relationship between socioeconomic status and gambling expenditure after controlling for these things. Same thing with verbal. So, okay, what's the first step? The first step is that we want to plot our residuals versus the fitted values. So remember what a residual is. A residual is a person's actual response variable, so their actual gambling expenditure, y sub I, minus what the model, this equation, predicts. So, right, we make these predictions, and this is done in R for us by literally plugging in. So for person, let's pick a person out of the data set. Just randomly, we'll pick this person, this female here, right? Whose gambling expenditures were 19.6 pounds. I think that's per week, right? Forgot. Per year. Okay, well, that's not that much. So how would we get that person's, what would we predict for that person? Well, that person, if we look at the data set, and I'll just pick that person out here, we can actually print the whole data set down at the console by just typing teen age, teen gamb. And so we see that was case number 5. Okay. So what we would do is just take the predictors. So this is a female. Socioeconomic status is 65. Income of 2. Verbal score of 8. We plug those things into the equation and multiply by the constants there, right, which we get from the model, so the model coefficients, and we'll get a predicted value for that person. So we'll go ahead and do that just to demonstrate. So let me this up here. Actually, it's kind of hard to see, so we'll pick out the 5th row. I'll print everything again so we can see it. So we'll do summary, and then teen gamb row 5. Right. Okay, perfect. So we've got to do 22.56. So this is going to be a rough estimate, and the computer would do it with all the decimals. So it's intercept, okay, minus 222, or 22.1183 times 1, and we've got to there, so we get the negative sign, plus the coefficient for status, so that's 0.052 times their status, which is 65, plus 4.96 times their income, which is 2, and again, it's plus a negative, but we'll just do minus 2.959 times their verbal score. Okay? So the predicted our prediction here is actually a negative number, which is not great. Whereas this person uh, was did quite a bit of gambling. So we're pretty far off in our modeling here for this person, right? And so the residual for this person is, right, their actual y value, which is 91.6, minus a negative 9.930. So this person's residual is 29.53, right? The residual is positive because the prediction is lower than the actual, right? Our residual is negative if our prediction is too high, right? So we can plot, by the way, first of all, you can get all the model residuals, right, by resid gam, fac. So that's everybody's residuals. So we can see, we must have computed something incorrectly here. Oh no, that's correct, right? So we see we're a little bit off because of rounding error. So the computer computes it with all of the decimal places, so pretty close. Right? So we can plot those predictions on the fitted values and a number of other things using the plot function. So just to show you, if you actually do this, if you do plot gam on fac, what it's going to do is actually makes 4 plots. You can pick out each one, which I've done in the output. But if you just typed it at the console, you hit return to see each one. So this first plot, which you see on website, is residuals versus fitted. So what we want to see in this one, again, the two assumptions for interpreting linear regression. Interpreting meaning these assumptions enable us to make good inferences. Right? The first assumption is that the expected value of the residuals given x or the predicted values should be 0, right? So that means that we should see most, if we could, most of the residuals close to 0. Sometimes they can be quite far away, and that doesn't matter, right? It's expected value. So the expected value of residuals should be 0. They can be spread out as they are here, but the second assumption is that the variation or the variance in residuals should be constant across all fitted or x values, right? So no matter what your actual fitted value was, or what if we just plotted this on income, right? So we can do that too. I'll show you that in a second. So if we just picked out income or sex or verbal, what we want to see is we want to see for all values the spread to be the same, and we don't see that. So this plot is telling me that the assumption of constant variance is violated, right? Because here, so for small fitted values, there's not a lot of variation in residuals, right? They're all kind of, sort of spread the same. As our predicted amount of income goes up, see this kind of funnel shape here? It starts to open up where we are more variable for these larger values. That's no good. That tells us we've violated the assumption of non-constant variance. It's a very important assumption because it helps us define the p-values and confidence intervals that we would use for inference. And so if non-constant variance is violated, sometimes we have to do a couple of things to make those really the standard error, the model standard errors, which go into the confidence intervals and p-values, need to be corrected in some way. If you scroll down on the page or you hit the next plot, this is a plot that is also important just for inference. So this is the classic QQ plot where we make the assumption that the residuals should be normally distributed. Now that's not an assumption that is necessarily that we need for linear regression in general. Again, it's an assumption that we need for our significance tests and for our confidence intervals. So again, if you want to interpret the p-values and confidence intervals from your model in a robust way, you need to check this plot. What we want to see is we want to see this dotted line on a diagonal, and we want to see all of the points. These are all of our residuals. We want to see them all nice on that diagonal line. Okay, we don't see that. Okay? So if they're all on the diagonal line, that means that the residuals are in the same order they should be if they were normally distributed. So when we see a plot like this, we see that the residuals are not where they're supposed to be. It really looks to be only 3 values that are driving this violation. So that the residuals are not quite normally distributed. They're close, but not quite. And so we might take some caution in interpreting the confidence intervals and p-values from this. The third plot is similar to the first one, but now the residuals have been standardized. And so you can kind of see that what this does is sort of zooms in on the first plot. So the first plot, whoops, okay, it's not letting me go back. We can see it right here, right? The first plot, everything's kind of tight. When we standardize the residuals, we still see some violation of constant variance. We also see this on each one. You can see the this non-parametric regression line. That's trying to clue us in. In both cases, it's curvilinear, which is not great. They're trying to clue us in if we've got a really bad curve in it. So again, this doesn't look awesome as it matches this plot in the sense that we look like we've got something not right with the residuals. And then the final plot that you get, there we go. Final plot is are the residuals versus the leverage, as well as something called Cook's distance that you learn about in the text, but we'll explain it a little bit. Right? So right, we've kind of stepped through this now. Let's talk about that last plot, leverage and influence. So this involves a little bit of matrix algebra. It's not super important that you understand, but essentially the equation for fitting a linear regression model has a closed form. So basically you can take the values of your x variables and the values of your y variables, step through this matrix equation, which will yield a vector, which in this case will have, I forgot how many predictors we've got, including the intercept. That vector will have 1, 2, 3, 4, 5 components. And so if you solve this linear equation, you will get a vector called beta, which the entries are the intercept and the regression coefficient. This here, this part, is a matrix. Y is a vector, meaning it's just got one column. It's one big long column of numbers, the gambling expenditures. This is a matrix that results from multiplying x by its, so x is all of the columns, the other variables in our equation that we see here. Right? So 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4 plus the intercept. Right? These columns of numbers here are x. And so this equation says if we flip x around a couple times, we create a matrix of x kind of multiplied by itself in this strange way. We invert it and then we do it again. That whole thing is a matrix, which we call H. It's also known as the hat matrix because it's the thing that puts the hat on Y. It's the thing that turns Y into its predicted value. Right? It's basically just a way to kind of represent the transformation from Y into its predicted values. This matrix has on its diagonal entries that we call leverages. Leverage is based on the fact that even though the errors of the regression model should have constant variance, right, sigma squared. In fact, the residuals in our model will not, right? The variance of the residuals will vary a little bit according to each individual observation's leverage value. Okay? In this equation, right, large values of H will exert more leverage because they make the variance small, right, and force the fit of the line close to it. So leverage values are values in your data set, Y values specifically in your data set, that sort of force the fit of the regression line close to it. So often this is often that observation can be an outlier, usually at the sides of the plot. And so what can happen is if a point has large leverage and you delete it from the model may change substantially. It also gives us points to look at where we might have a problem with the variance assumption. Related to leverage is something called Cook's distance. So looking at a leverage value itself is not going to be particularly illuminating. So Cook and Weisberg devised a different number, which makes use of what are called standardized residuals. We just looked at those, just puts the model residuals, which are on the scale of Y, in this case, gambling expenditures, it puts them on a common scale. And essentially what the distance value is for each Y is the difference in the model prediction, or the squared difference really, in model predictions between a model with that value and a model without it. Okay? And turns out that in ordinary linear regression, you can compute that using the leverages and the squared standardized residuals. So this basically represents a change of the fit if you drop a particular case from the data set, right? Basically, it's a distance. How different, or what's the distance between one model and a second model, where one model has, let's say, case number 5, which didn't fit very well. What if we dropped that case from the model and reran it? Cook's distance tells you how big the difference will be. So just like leverage, and because it's based on leverage, small leverage usually will also mean small Cook's distance. Okay? So that final plot, leverage is on this axis. So these are all the, for all the residuals, these are the leverage values. And then these contours here give us the sort of boundaries of Cook's distance. Okay? So this actually is not telling me anything really that bad. The only issue here might be row 24 in the data set. Let's go ahead and take a look at row 24. Here, this person. Okay? Yeah, so this person clearly has among the highest gambling expenditures. Okay? The male, that's not surprising. So what we look at is like, is their income really low? No. So sometimes with Cook's distance and leverage, it can be a weird combination of X values, right? In this case, we have actually, what we have is just a large gambling expenditure. So if we delete this person from the model, our coefficients might look a bit different. Now, it's tough to say, because this is a small data set, this person's right on the border. Again, these are judgment calls. So, if you were interested more in creating a predictive equation, right? So you wanted to actually, I don't know why you would want to do that, but predict someone's gambling expenditures. Maybe you're working for one of the 5,000 companies that bombard us whenever we watch TV, FanDuel, whatever it is. You want to predict someone's gambling expenditures, market to them. If you leave this person in the model, you might get different predictions than if you take them out. So again, that's a judgment call. So we might say, I'll leave that person in and qualify that we have, a fit that might be sensitive to it, so on and so forth, right? So again, here's our folks with distance greater than 1. We can also see that we're off with both of these. So the other person is 39 down here. So of the 2 leverage points, 24, our prediction is too low, and 39, our prediction is too high. This person, status, high status, lot of income, it's male, but they only spent $6. This person's low status, high income, right? Really high gambling expenditures. Okay? So again, there's really nothing that you should do in this case. It all depends on your goal. If you want to get things exactly right or overfit, you would leave it in. You might take these out if you were looking for more generalizability. What you don't want to do is to start to put cases in and leave them out, and to try to force a p-value to be small or large, right? That's called p-hacking. That's what you don't want to do. And so as long as you're not doing that, and if you're reporting it in an article, as long as you're clear that, hey, we found 2 high leverage values, we ran the data, we ran the model without those 2 values, and sometimes everything looks very similar, and we say, okay, the substantive conclusions didn't change. Females still spend much less than males. Income is still positively related to expenditures, and you're done. Sometimes, they look really different, and then you have a quandary. You might, in an article, give both sets of observations. Reviewers are all over the place with whether they care about that, whatever. That's just sort of what you should. There's no like hard and fast rule of like, do this, don't do that. It's all based on your judgment. All right. So with ordinary least squares, again, these 4 plots are the standard plots that come out of R. You can make other ones, right? So in some cases you might want to, and I'll just kind of show you an example. You might want to take each of the predictors, status, income, verbal, and check the residuals against them. So we'll do this for sex, and we'll do it for income. So the way to do it for a factor would be we would make a box plot. So we do a box plot on the, let's see, we'll do resid, gam, and we'll do that on team, gam, sex fac. So what do we see here? The plotted on the box plot are the distribution of the residuals, model residuals, for males versus females. So we see another potential violation here that there is not constant variance in residuals across males and females. So there seems to be some relationship perhaps between model residuals and sex. That's not great. And we've already kind of seen that basically this is telling you that the range of gambling expenditures is larger for males than it is for females. Let's look at how it looks for income. So in this case, instead of box plot, we'll use a regular scatter plot. So we'll do plot resid. Actually, we want to do on the x-axis, we want to do the predictor. So we'll plot teen gamb. Or actually, we can do it with the formula interface. So we'll do the same thing. We'll do resid gamb mod fac on teen gamb, in this case, income. Okay. Now this looks a lot better. Again, we've got that person, that's person 24 again. But this looks a lot better, even than the full model, right? Very flat, right? Very much sort of all the residuals are contained within a box, except for that one. When you've got only 1 or 2 that are kind of bucking the trend, usually that's okay. Again, you want to investigate what's going on with that person. Sometimes it's a data entry error, right? Instead of 156, it was supposed to be 1.56. You might never know, but that's just sort of things that happen, right? Okay. Good. So again, with ordinary least squares, most of what you need to do is just eyeballing plots. Again, um, the assumptions that are able to be checked with plots are that, again, the residuals have constant variance. The expected value of residual is 0. There's no relationship, no linear relationship or otherwise between the residuals and the fitted values, or between the residuals and the predictors themselves. In this case, we see some violations. We see sort of a kind of a little bit of a curvilinear relationship when we plot fitted on for residuals. We also see some non-constant variance, right? Wider here. When we look just at income, it looks a little bit better. For females and males, again, non-constant variance, but at least the residuals are centered around 0 as they should be. All right. Now for logistic regression, it's a little bit different. We'll use the same data set that you used for homework 3, that's the birth weight data. And so again, we'll fit a model where we're going to use, we're trying to predict low birth weight with race, smoking, the weight of the mom at the last menstrual period, and the number of physician visits. It's a logistic model. We get the output. We see there's perhaps a couple of relationships in there, so on and so forth. We get our odds ratios. We could do our test. And so there's a couple of things you can sometimes use what's called the residual deviance test, which is a chi-square variable. But in logistic regression, it's harder to do, but you can approximate it using something called the Hosmer-Lemichaud test. Now, most people don't like this test either, and there's a better way to do it, but it's instructive to see how it works. Okay, what this test is really it's sort of it's a goodness of fit test between the model predictions, which remember when in logistic regression, we can transform the predicted values, which are logits, can transform them into probabilities. And so what this test entails is you have to group your data. Okay? So across some set of groups in your data set, by default, this test uses 10 groups. So you group your data based on the predicted probabilities. And this test is basically how good is the fit of the predicted probabilities of those 10 groups to the actual proportion of ones in that group, right? So in this data set, a 1 is a baby with low birth weight. Right? So so let's take a look at this just so you can see the machinery of it. So I got to fit, first of all, fit my model. Put it up. And I'll just fit the model because we already saw the rest of the summary. Okie dokie. So the first thing we're going to do is we're going to make two new vectors, okay? Y and Y hat, okay? So Y is just the fitted values from the model, okay? So if we look at Y, it's just a bunch of zeros and ones, okay? 0, 0, 0, 1, 1, 1, blah, 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 okay? So, and we have, if we sum Y, it tells us how many low birth weight babies we've got in the data set, 59. The reason I take it from the model fit is because there was some missing data, right? So just make sure we've got the same thing, okay? Y hat are the predicted values. Now these are probabilities. So if we look at Y hat, these are probabilities. If we instead, right, fitted values. If we instead looked at the linear predictor, we would see something different. So within the birth weight model here, okay, the fitted values of probabilities, I forget how we actually get the linear predictors. So if we did mod 3 linear predictors, these are the logits, right? So this is the number that you would get if you use the regression equation. And then, so for case 85, a logit of negative 1.20 corresponds to a probability of low birth weight for that case of 0.23, right? 23% chance. Somebody with those covariates, we would predict them to have a 23% chance of a low birth weight baby. So what happens? So what we do is first, the predicted probabilities are ordered. Okay? So we put everybody in order, as if they're not in order yet. And then what we do is we split the data into 10 equal parts, okay, based on those predicted probabilities. So we've sorted our data. We split it into 10 groups. Within each 10 group, we average the predicted probability. Okay? So we get an average predicted probability. And then what we do is for those same people in that group, we essentially compute the proportion of those people who actually did have low birth weight babies. And the Hosmer-Lemmy-Show test uses a chi-square type relationship, right, to see if across those groups, right, it actually uses numbers. So YJ would be the number of babies in that actual low birth weight babies in group J, subtract off MJ, the number of people in that group, times probability, the average probability in that group. That gives us an expected count. So it's observed minus expected over variance, right? It's a chi-square-ish thing. Okay? Add that up over 10 groups. If the number is small, it means the model fits. If the number is large, it means the model doesn't fit. It means essentially that the predicted probabilities, when we transfer them into predicted counts, are very different from the actual number of low birth weight babies in those percentiles, in those deciles. So all of that can be done using the Hose-Lem test function in the resource selection package, which is the only place I could find it. There's other places for it. So you'd have to download this. And I run it. And I can see for this particular piece, and again, if you wanted to take a look at, there's lots of stuff in there. Again, it gives you the observed counts, the expected counts. You can take a look at that across the 10 groups. Degrees of freedom of the test is the number of groups minus 2, and which gives us a chi-square distribution as a reference point. Our actual observed chi-square is 7.89, which is consistent with the null hypothesis. The null hypothesis meaning that the model fits, right? Null hypothesis is there's very little difference between model prediction and observed count of low birth weight babies in these groups that we made. Okay? So that's one piece you can use. Now, people don't like this test because it's only using 10 groups. It's rather arbitrary. So there are, this is a test which in the prediction literature is known as a calibration test, right? Is your model well calibrated to the predictions? Are your model predictions well calibrated to reality? Do they match reality? And so there's all different ways you can do that. This is a quick and dirty one. There's other things you can do. Another approach, also somewhat controversial, are the adaptation of those variance accounted for sort of R-squared like statistics to logistic regression. I'm not going to go into a lot of detail about it, but essentially, there's some problems. And I talked about the Nagle-Kirky R squared before. The equation I did not print here. It's in our older notes. Okay? So it turns out you can get that number using pieces from the model. Okay? So if you look back at your notes, it's a fraction, 1 minus e, right? Where we raise e to the difference between model 3's deviance and a null model deviance divided by n. Right? And then the denominator is 1 minus exp to the negative null deviance divided by n. Okay? That gives us 0.139, or 14% of the variance in birth weight is explained by the linear predictor. Now that seems very small. The reason is just because it depends on a number of factors that these R-square approaches to binomial data will often be much lower, much farther away from 1.0 than you might get in an ordinary least squares regression. And we'll just leave it at that. There's reasons for it. Finally, the residual plots for a logistic model are not helpful. As you can see, this looks weird. The reason it looks weird is because the residuals can either be 0 or 1, right? So errors are binomial, right? That's why we use the binomial model. And then the linear predictor is not linear, actually, when we exponentiate. So you get this kind of weird thing. If these lines are relatively parallel, you're kind of good. This isn't terrible, but this plot usually is not super helpful. One piece that some people use, and Faraway's written a function for it, is to plot the so-called half normal residuals and use a QQ plot. So again, we'd want to see the diagonal. We don't see that. We see one outlier there, and that is telling us that there is a leverage point, and it turns out that that's a person who does have a low birth weight baby, but maybe kind of wasn't at that much risk, or did so. Sort of actually it looks like an outlier on the utilization variable. For comparison, here's a random other case that looks a bit different, right? These things are the same, but this person didn't have a low birth weight baby, but they also didn't go to the emergency room. Interestingly enough, the predicted probabilities for these two are very similar. And so, we might say is that person is 68 is just, we might want to watch out for this person or this model, because this person had a very high number compared to everybody else. Here's the basically the 5-number summary with the mean of the number of healthcare visits. This person's like way, way high. There's only one person with a greater number of visits. So in this case, what we might do again is say, our model may be influenced by this person with a large value for utilization, and we can do the same thing as we did before. We can go ahead and refit the model without that person. If you want to know how to do that, by the way, is a couple of ways to do it. So I'll actually just write some code down here. So one way to do it is we go back up to the model equation, I'll just copy it, is to use the subset command, which you can use within GLM. So A, and then you can do subset. And in this case, what we would do is you could do a number of things. You could do let's say we don't want either of the people with high utilization. We could do, let's see, what is it? We only want FPV less than 3. So now that this is going to give us something different. So we'll do coef mod 3A and coef mod 3. Okay. So we do have some changes. Obviously, the intercept changes. Without the high utilization people, FTV's coefficient actually gets larger, it's further away from 0. With those two people, it gets smaller, interestingly. Everything else looks fairly similar, right? So the coefficient for race, black versus white, the contrast between black and white, other and white, smoker versus non-smoker, they look pretty similar. Low birth, the weight at the last visit looks similar. So deleting cases, in this case, right, we could compute Cook's distance if we wanted to. It's a more complicated formula. Just showing you some things you can do. So I use the subset command there. Another thing you could do is just save the data set. So you could say, let's make a new data set. So birth 2 is birth weight. And what we don't want is or we can do the same kind of subset stuff where we want all rows for which birth weight F is less than 3, comma. And so we can see birth weight 2, so we drop more than 10 cases. And so if we look here, we're going to find only 0s, 1s, and 2s in the FTV column, whereas we've got a few people. There's a 3, another 3. We should find the person with 6, somewhere is 4, so on and so forth, right? So that's 2 ways to, and then you would model 3B, be the same thing, but now instead of subset, we would just change the data set that we're using to birth weight 2, and we should get the same results, coef mod 3B. Yep, same results as the other one. Okay. All right, so to bring this all together, what we've done is to start to not accept our model results as the gold standard. Instead, look at some pieces of information that might give us a sense that our model is really, really wrong. And so again, what we're trying to do is to assess how wrong it is. If it's only a little bit wrong, if the assumptions are only a little bit violated, that might be good enough. Different cases will require different approaches here. With ordinary least squares, it's very straightforward. There's some simple things you can step through. With generalized linear models, with mixed models, it's a little more complex. There are some new developments that have come around in the last 10 years or so that make it a little bit easier, but they're very computationally intensive. So we'll touch on them briefly later, but that's it. So again, we will return to some diagnostic procedures. Actually have to update that with this new piece of information, and I'll do that in the subsequent week. So that's it for now. I'll check in with y'all next week. All right.